Hello everybody. In this video, we are going to walk through semantic segmentation. So this notebook is going to teach you how to do semantic segmentation using Torchvision. But first, what is semantic segmentation? So you have this image of a person riding a bike, and if we want to do semantic segmentation on it, we want to assign a label to every pixel of this image. And let's say we have three classes. Here you can see that we have the human class or the person class, we have the motorcycle class, and everything else is the background, right? So we want to extract all the masks for the three classes. So you can see here, we have extracted it. This is the output of semantic segmentation. We have colored all the pixels that belong to the background black. We have colored everything that belongs to this motorcycle, greenish, and this one kind of pink. So now this is, if you think about what we have learned so far, we learned about image classification, we learned about object detection, and now we are learning about image segmentation. In image classification, for the entire image, we had a single label, right? And in object detection, for the image, we had several bounding boxes where we detected object. And for every object, we had one label, all right? So we went to a higher level of granularity, right? Because in the first example, in image classification, even if you had multiple cats, you would call this entire image cat, right? There was no way to know how many cats were there. And in fact, if there were, a few cats and dogs, there was no way to say whether the label should be cat or a dog, right? So image classification has its place, but object detection is much more useful than image classification, because there we can find a region, create a bounding box around it, and assign a label to it. So that's a higher level of granularity. Now you can take it even further, right? You can say that the bounding box doesn't capture everything I want, right? The bounding box is not enough. In that case, for every pixel in the image, we need to assign a label to it. So here, this pixel, every pixel has a label, right? It's either 0 or it is the colors that are determined by this person class or this motorcycle class. Now, image segmentation traditionally was done using many different methods. Some of them used color and texture, etc. And you can see that color-based segmentation would completely fail in this case, because the person is wearing the same color as the motorcycle, so color doesn't cut it, right? So that is why we have to use something called semantic segmentation. The word semantic means meaning, which means that it is sort of an intelligent kind of segmentation. We are looking to segment objects instead of colors and textures, etc. So it's a higher level of abstraction. So there is one issue with semantic segmentation, which is fixed later on. But for every class, for every pixel, we have a class label, right? Which means that there could be two people. All the pixels that belong to those two people would be colored the same, right? And that is why, semantic segmentation, you can take it even further and create another thing called instance segmentation, where every instance of the same class, they would have, we can identify that these pixels belong to this object and this pixels belong to this object. In semantic segmentation, you cannot. They would be assigned the same label, person, but you cannot say which pixels belong to this person and which pixels belong to that person, all right? But there are still a lot of benefits of semantic segmentation. So let's start going through it. By the way, if you are looking for a career in computer vision and AI, and you're able to solve these three problems with a very high level of accuracy under many different conditions, image classification, object detection, and semantic segmentation, it is almost sure that you will land a very good job in the industry. Because many, I would say 80–90% of the problems in computer vision can be boiled down, can be framed as one of these problems, right? Either a classification problem, or an object detection problem, or a segmentation problem, all right? So some of the applications, some of the most common applications are autonomous driving. For example, if you want to build an autonomous car, you need to find where the lanes are. You need to find where the sidewalks are, or where the people are moving, right? Where the sky is, everything you want to know about that entire image. So it's very important for autonomous driving applications. So it's, object detection is not sufficient. You cannot say, oh, the lane, I just want a bounding box around the lane. That's not sufficient, right? And that is why you need semantic segmentation. If you want to do any kind of facial analysis, right, you want to segment the face into eyes, nose, lips, hair, skin, etc. So that way, let's say you want to do some skin processing. In that case, you can do semantic segmentation and focus only on pixels that belong to the skin. You can also do indoor and outdoor segmentation, so that you can use that information to do further processing. For example, this is the picture of a bed, right? And this is a semantically segmented bedroom. You can say that, okay, this is part of the bed, these are the pillows, this is the lamp, and so on and so forth. Can be very useful in image understanding. When you want to look at satellite images or even drone images looking down, and you want to identify where the parking lots are, where's the swimming pool, where the residential areas are, or where the roads are, you can do those kinds of things using semantic segmentation. The possibilities are endless, and one of the big areas is also medical image analysis. Those images, MRI scans, or you have pathology images, they need very high quality segmentation so that you can figure out which parts of the image belong to maybe healthy tissue or cancer tissues, etc. So the possibilities of semantic segmentation are just endless. We are going to use Torchvision for semantic segmentation, and here's the input, right? First of all, when we use any model from Torchvision, we need to normalize our images based on what the model was trained on, right? So we need this value, mean and standard deviation. So as we have mentioned in previous notebooks also, the mean needs to be subtracted and the standard deviation needs to be divided from the image. So this basically, when you subtract the mean, you're normalizing for brightness. When you divide by standard deviation, you're normalizing for contrast, so to speak. Now, the input to a network that is available in Torchvision, this is the dimension of the input. We have the number of the batch size. The batch size, you can actually use a single image, but you can also send 10 images, 20 images, whatever you want for processing. So the batch size is basically how many images you're sending. Then we have the number of color channels, and then we have height and width of the image, okay? The output is also the same sized image, right? The height and the width is the same size as the input, right? So this is the same. The batch size is also the same. So the same number of images are returned to you. The number of channels in the output depends on the number of classes, okay? So there is one channel per class. So you can imagine that we are returning, for every class, we are returning a mask. In this example, for this, you would have 3 channels. The background class, which would be black which would be actually white for areas which are background. The person, and it would be black everywhere else. The person class, it would be white only for regions which contain the person class. And the motorcycle, it would be white only for regions which contain the motorcycle class. Everything else will be black. Now, this particular image, you can see that, oh, this doesn't look like what I'm describing. The reason is that we have color coded. We have taken that information, those masks, and then we have done a color coding to represent. Otherwise, we'll have to see 3 images, right? Instead of seeing 3 images, we could color code those and combine them, and we'll show you the code how that is done, so that you can see the entire information in a single image because it is color coded, okay? But the output, the raw output of this is basically the number of channels, right? You have the same height and width for the image. You have the same number of images, which is the batch size. The number of channels represents how many classes there are. And in the example that we are going to show, it is going to be 21 classes. Okay. So with that out of the way, let's look at FCN with ResNet 101 backbone. So FCN stands for Fully Convolutional Networks. And this is one of the earliest neural networks that was deployed for semantic segmentation. We also mentioned with ResNet 101 backbone. So basically ResNet is ResNet is a very standard architecture, and it is a bank of convolutional layers with skip connections, etc. that is very commonly used. It comes, some popular flavors of ResNet are ResNet 50 and ResNet 101. ResNet 50 is a smaller model with 50 layers, and ResNet 101 is a larger model with 101 layers. Because these form the backbone. These are extracting the features, and then you do something on top of it to create FCN. So the FCN architecture, you can swap out, the backbone with ResNet 50 or something else, and it would still be an FCN network. So in this example, we are going to use ResNet 101. Here we have some standard imports. Torchvision, from Torchvision, we are importing the models. Then we have PIL to look at images or read images. Torchvision, we have gone over these things before also. Matplotlib and Pytorch, and then we have requests that basically allows you to download stuff. Okay, so first we load the model, and basically from the models class we know that this is a standard model inside Torchvision, right? So inside segmentation, we have FCN underscore ResNet 101, and you could also try ResNet 50 by changing the name here. Then we say that, okay, the weights that we are going to, that's the model architecture, but the weights are also, we are going to use the default weights, whatever they have trained and given us for free, we are just going to use it. So we basically load the network using this call. So you can see that if the network is already not cached on your machine, it is going to download that and it becomes ready. Okay. Now we also have a utility function here. I'm not going to go over this because this has been used several times. This basically allows us to get files, images and other files, and that they get downloaded to your instance of this collab instance. Okay. Then we have a directory called inference directory, inference underscore dir. This is where we are going to load, save all the images, download all the images, all the information that we do for a particular image, it will be stored in this directory. So we just create that directory. Next, we download the file. This is the file of a bird, and we are basically downloading it from the internet. And then you can see that we are displaying that image. All right. So once that has been done, this image could be of any size, but we want it to be of size 224 by 224. And for that, we do it in two steps. First, we resize the image to 256 by 256, take the center crop, and then we convert it to a tensor, right? The tensor, while converting it to a tensor, we want to normalize it between 0 and 1, as we have done several times. So we are not going to go over that. Basically, the image while training had been normalized, and therefore we have to do the exact same process during inference. So so the image, which is typically between, the pixel values, which are typically between 0 and 255, they get normalized to 0 and 1, right? So that's one thing we have to do. And then we basically subtract the mean and divide it by the standard deviation. This, obviously, it is done automatically for us using the transform class. Let's just look at this. So while composing, we resize the image, we center crop the image, take the 224 by 224 pixel values from the center, because this is what the network was trained on. Then we convert it into a tensor. When we convert it to a tensor, it converts this, it does this normalization From 0 to 255, it takes you from 0 to 0 and 1, and it also converts it to floating point. And then we normalize the image, subtract the mean, and divide it by the standard deviation. And finally, this image needs to be, before we can pass it to the network, it needs to be it needs to have batch size of 1. So the size of the tensor needs to be 1 more than the image size, right? So image size is typically 3 by 3 is the number of channel, and then height and width. But because we are passing one image, we need to unsqueeze it. So add an extra dimension just so that it is compatible with the network. So once we have done that, we are ready. We are ready to pass that input image that we just created to the network FCN and get the output, right? So this basically, this field output contains the output. We do that and we look at the shape. The shape is 1 by 21 by 224 by 224. 1 is the number of, it's the batch size because we are going to send, we sent only one image. 21 is the number of channels, 1 per class, right? So there are 21 different classes, and then we have a 224 by 224 image, all right? So we are in good shape. Now you may be wondering, what are these classes? Okay, so let me show you some code where we decode the segmentation map. As I said that if you look at the output, it has 21 channels, right? But it's, and every channel, if you look at the motorcycle class, the pixels which are motorcycle would be 1 and everything else would be 0, right? But there are 21 of those. You're not going to look at 24 different classes on your screen. So we want to create a mapping. We need to have a color map attached to this. So this is the color map we are going to use. For background, we are going to use black color. For aeroplane, which is the first class, we are going to use kind of half red color. This is like a darker shade of green, and so on and so forth, right? So different colors are used to represent different classes. I jumped ahead slightly because I wanted to simplify things and tell you the whole story in just a bit. So here I jumped this step. Now let's look at this, the output. The output that we received here is 1 by 21 by 224 by 224. That's the height and the width. 21 is the number of channels, and 1 is the extra dimension for batch. First of all, we don't need that. We are going to squeeze it out, right? The second thing is that we are going to detach detach this so that the whole computational graph is dropped. We don't need it for inference. We are going to move the memory to CPU, and then we are going to convert this to a NumPy array that resides on the CPU. Also look at this part, right? Where we have 21 channels. For every pixel, we have 21 channels, right? So just think of it as a pixel having RGB colors, but instead of RGB colors, it has 21 values. And initially, if you have an ideal segmentation model, the motorcycle class would be 1 for that pixel. If the pixel belongs to the motorcycle, the class label would be 1 for the channel that represents the motorcycle, right? Actually, let's look at the bird example. So because we have a bird here, so all the pixels that represent the bird class, they would, one second. Okay, so all the pixels that represent the bird class, they would have in the 4th channel, right? 0, 1, 2, 3. Sorry, the 3rd channel, the bird pixels would light up, right? They would be 1, and all other pixels would be 0. But in other channels, right, the pixel that corresponds to bird, they would all be 0, right? That's the ideal case. In reality, these are class probabilities, right? These are class probabilities which explain what is the probability of this pixel belonging to this class. For if we have a reasonably good model, in that case, the bird class will be the highest. It will be between 0 and 1, something like 0.9. but it may not always be, it will not be 1, right? Other classes may have a little, small probabilities like 0.1 or 0.05 or something like that, right? Especially you can think about 2 different classes like cats and dogs. In that case, even if it correctly identifies that it is a cat, the probability would be 0.75. The dog class could have probability 0.25, right? So these channels basically encode class probabilities. So we need to do an argmax. When we do an argmax in this step, we are extracting the class which has the maximum likelihood, all right? The most probability. So we are creating this output image. We are creating this output map where it's basically 224 by 224. That's the size of this output image. And for every pixel, we are putting a value 0 through 20 inside it, right? So that if the value is 3, it means that this pixel belongs to the bird class. If it is 0, it belongs to the background class. If it is something else, then it belongs to that particular class. So here we are now printing out output maps. And you can see that the shape is 224 by 224. So it's like a grayscale image. Now we do what are the unique elements in it. We see that there are 2 unique elements. One is 0 and 3, which means that the image consists of only 2 classes. Class 0 is the background and class 3 is the bird, as we can see here, right? So now this is the map that gets decoded, right? So we send the map to this decode underscore segmentation map. And here you can see that it is assigning, it is mapping the class label to the correct color, right? So this map that comes in, this is actually not an image, but it is a map like this, right? It is a segmentation map that comes in, and we are using our color mapping to map those colors, map those numbers into colors. And here you can see that it goes in a for loop and assigns colors to these numbers between 0 and 20. So if the number is 0, it assigns the black color. If it is, if it is 1, then it assigns this dark red color and dark green, and so on and so forth. And once you have done that, you're basically stacking this into an RGB image and then returning that image. All right. So that's what the function did. So, okay, so we get this RGB image and we are going to plot it, right? And once we plot it, there is this, the third image is essentially this color, right? And that color, you can see that the background is black, and that color gets applied to all the pixels that belong to the bird class. All right. So that's what we did, right? That's how the results we got. We can also put all this thing that we discussed in a single function. We call it segment, which takes in the network, which takes in the path, which takes in a parameter which says show original image, and then it says that use the CUDA device, which is the NVIDIA GPU, while processing this, right? So we first create an image or a figure that will display the image. We display the image, and then we basically take the image and resize it to, depending on what is the size of the network. For FCN, this would be 256, and you have to do a center crop. For some other, you would have to do, you'll basically do it something else, right? So now you pass in the mean and standard deviation, and you unsqueeze, as we had mentioned. You get the input image, and then you basically get the output. From the output, you get the output map. You decode the output map so that you can easily show, so that the results are shown in a single image instead of a 21 channel image, and then you show the map, right? The segmentation map in a single RGB image. Okay, So now that we have everything set up in this segmentation class, now that we have set up everything in the segmentation function, we can simply use it. We can download an image. Here we are downloading the image of this horse, and then we are passing the FCN network as well as this path, and everything remains the default. As you can see that it comes out with this beautiful segmentation of the horse. We can also use another model called DeepLab v3, and DeepLab v3, to get that model, DeepLab v3 also can have multiple backbones. We are using the ResNet 101 backbone. It also comes with the ResNet 50 backbone. ResNet 101 would be a larger model. So we first get the model, we get the weights, and then we basically get the network. So it automatically downloads the network. We can pass in the segmentation, pass it for segmentation. And you can see that this also produces a nice segmentation map. And you can do this for any image. You can change the location of the image here if you have an uploaded image somewhere, and try it out yourself. So in this class, one, there are different classes, right? There is the person class, and then we have the dog class, and we can see how this works out. So pretty decent, right? You have the background class, multiple people here, and then we have the dog over here. It also detects these ones as people, which is, it's pretty blurry, but it looks like a person to me. So that's interesting. All right. So you can also compare, right, with FCN as well as DeepLab v3, the two segmentations. Here the quality looks about the same to me. Maybe DeepLab v3 does a better job around this. So you can see that FCN, the shoe is being mislabeled as the dog, and FCN does a better job, right? It still doesn't put it as the person's body part, but it does not think that it is part of the dog, right? So in general, DeepLab v3 gives much better results than FCN, and the computational cost is about the same, even though they should actually use DeepLab v3 should be more expensive, but when we do in the real world, it's about the same. It's about the same. So here we have some code for comparing the inference time. Again, this takes in the network, it takes in the image, and it outputs the time it took to do the inference, right? So here we want to make sure that we don't all the pre-processing that is being done to the image, the loading of the image, etc., that doesn't get in the way. So we basically start the time right before we send it to the network, and then we estimate the time, right? End time, and return how much time it took. So again, when you are doing these kinds of processing, you should always, you should never do it, only a single time. You should run it 100 times, 1,000 times, etc., so that you get a good sense of how much time it is taking, because the first time it can actually take a long time. It's loading the model, it is loading the images. There's a lot of things that happen on the first run. So you should run it for, let's say, 100 times, and maybe even discard the first run and average over the rest, right? This code allows you to do the inference over CPU. You can see that it is running for 100, and it gives you the average here. Similarly, you can do the for DeepLab v3 and compare the results. You can see they are about the same, 1.55 seconds versus 1.72 seconds. That's not bad, right? They are about the same. If you run it on the GPU, sometimes, in this case, in our run, it showed that DeepLab v3 is slightly faster, but that's not always the case. It's good. The right conclusion here is that they're about the same, right? The processing power is about the same. So yes, so you can see here that DeepLab v3 is slightly more expensive on the CPU and about the same, and slightly less expensive on the GPU. but they are about the same, right? They're going to take about the same amount of time. So now you can work with these this notebook yourself, try out different images, see where these kinds models fail, and you'll get a good sense of the quality differences between the two models and what are the kinds of things under which these things fail. And make sure that your model, the image that you're trying to do inference on, it has these classes, right? Because otherwise it will be all background. If you give it an image of I don't know, something that is not part of this, then these 21 classes, then you will pretty much get black images all the time, right? So it depends on what your model was trained on. The pre-trained model that comes with Torchvision, they were trained on these 20 classes. If you want to train your own model, then it's a more you have to go deeper into how the training works, and those things sorry, and the training part is covered in our deep learning with Pytorch course. We go into great detail on how to train an excellent model, how to do model selection, how to do how to gather the data, how to improve the quality of the model by massaging the data, looking through your data, and then what is the training procedure to follow, what is the recipe to follow. All those things are covered in our course Deep Learning with Pytorch. But let's continue with this. This is also very exciting, this free course, because we are able to learn the basics, right? We are, of course, we are not training a very big model or anything, but we have to first take our first steps, and then we can run, and then we can fly, right? So that's all I wanted to cover in this module. See you in the next module. Thank you.